Hello, Mathematics for 83 students. I'm going to tell you today about no arbitrage pricing theory, which is a theory about prices in the financial markets and how prices emerge, what they are, if we assume that the market um, allows no arbitrage. Now, the word arbitrage, we will define it mathematically, but what does it mean in general? So, a situation where you can create some kind of a portfolio or trade where you don't take any risk, don't have to spend any money, but you make money, at least make money with positive probability. So basically, a free lunch, money for nothing. That's called an arbitrage. This whole theory that we will be discussing is based on the premise that this should not be possible. If there was somewhere in the markets where people could just make money for nothing using the Dire Straits song title, then of course everybody would want it. And when everybody wants it, then um, people take advantage of it and prices change and it's no longer free because people would buy up whatever is needed to make that free money. So the underlying assumption that we have in this theory is that in a properly functioning market, there should not be any money for nothing for anybody. If you want some money, you have to do some work, take some risk, do something for other people. That's the underlying premise. In this model that we will be discussing now, we will be discussing it in a limited context, although we'll expand it just a little bit later on. But in this basic context, we assume that there is a market, which is a one-period market, in which there are known prices of certain securities today, and in one period, at the end of the period, prices may be in a certain probability distribution. So they're uncertain, but there is some kind of probability structure that describes that uncertainty. We assume that in this one period market, typically 1 year, there are n securities, let's call them S1, S2 through Sn, that can be stocks, bonds, or any securities. We assume that they're all traded and have prices available, so we can observe their prices. We write omega for the set of m possible states of the world at the end of the time period. That's a one-period model, as I said, with omega equal to omega 1, omega 2 through omega big M. The price of security j at time 0 is written as S sub j of 0, and its price at time k at state of the world omega is denoted by S sub j of k omega. So the time 0 prices are represented by the kind of row vector that you see here, S sub 0, and S sub 0 is the standard notation for prices observed, the market observed at time 0. And they are S1 of 0, S2 of 0, up to Sn of 0, because we have n securities that are traded. N can be very large. It's just the number of things that are traded in the market. And the prices at time 1 are given by this matrix, where you see that the first security at time 1, so S sub 1 of 1 and then something, depends on the state of the world. And the states of the world are omega 1, omega 2 through omega big M. As you can see, all of the securities have those prices that depend on which state of the world we're in. If we buy theta j units of security j at time 0 with theta big theta, capital theta, written as theta 1 through theta 2 through theta n, and the portfolio is created that way, the value of the portfolio at time 0 is S of 0 times theta, so theta 1 S1 of 0 plus theta 2 S2 of 0 up to theta n times Sn of 0. At time 1, if state omega k occurs, the value of the portfolio is theta 1 S1 of 1 omega k plus theta 2 S2 of 1 omega k plus and so on up to theta n Sn of 1 omega k. So the general random value at time 1 looks like this, that there are n states of the world, and in each of the, I'm sorry, not n, big M states of the world, and in each of those states we have this kind of linear combination which represents the value of the portfolio, just like the one we just described. So for example, in state omega 1, the value of the portfolio is omega 1 times S1 of 1 omega 1 plus theta 2 S2 of 1 omega 1. It's again omega 1 because we are in state omega 1, up to theta n Sn of 1 omega 1. Again omega 1 because we're in state omega 1. And then you have the same for state omega 2 up to state omega m, big M. That's the number of possible states of the world at time 1. We assume that S sub j of k omega is greater than or equal to 0. So we assume that these securities are kind of like stocks, that they don't force you to pay money in the future. They may give you nothing or they pay you something. And that means that the investor's risk is limited to the amount originally invested. The amounts invested, theta j, may be negative, though. When that happens, it means that security Sj has been sold short. All of the amounts invested, theta j's, can be written as a column vector and referred to as this capital theta. Such a vector is called a trading strategy. So, for example, capital theta equal to 1, negative 1, 2 means that the investor has purchased 1 unit of security S1, sold short 1 unit of security S2, and purchased 2 units of security S3, and there are only 3 securities traded in the market. Security S1 will be assumed almost always, basically. Well, it doesn't have to be always, but it's basically almost always, to be risk-free. So we assume that there is a risk-free security. What does it mean to be risk-free? Well, it means that the security will pay the same amount at time 1, no matter what happens. In every state of the world, it will pay the same thing. So its value at time, not times, time 1 will be therefore S1 of 1 omega equal to 1 plus I, regardless of omega. Now we will formally define an arbitrage opportunity. An arbitrage opportunity is a trading strategy, theta, such that S of 0 theta is less than or equal to 0, which means what? It means that the price of the portfolio so created is less than or equal to 0. That means that you don't have to pay anything for the portfolio, or you may even get money for getting that portfolio. And then S of 1 omega times theta at time 1 is greater than 0, but this is a vector inequality, and it says that the vector on the left-hand side has all components no less than the vector on the right-hand side, while at least one component is actually larger. So the 0 here is a vector, and this is a matrix multiplied by a vector. The trading strategy itself is a vector of allocations to securities, and this here, every component of this resulting vector, we multiply a matrix by a vector, is non-negative and at least one is positive. In other words, for an arbitrage opportunity, the cost is 0 or less, but the payoff at time 1 is never negative and positive in some states. Arbitrage opportunity, therefore, means that the investor holding it has an assured profit without spending any money to earn it. The key insight of this theory is that absence of arbitrage means that prices are derived in a specific way, very much to actuaries' liking, because they will be calculated as expected present values under a certain measure. So they will look like actuarial present values. So the simplest market is a market with two securities. A riskless one, say bank account or risk-free security of some type, and a risky one, stock. Both sell for an initial price of 1, although that's just scaling. So you can set some other price, but we'll just scale it to 1. And at time 1, the stock either goes up to U or down to D, while the bank account is always worth 1 plus I. You can prove that an arbitrage opportunity exists if and only if 1 plus I is more than U. Thus, unless the bank account return is certain to be greater than the stock's return, the market is arbitrage free. So if we have a trading strategy, theta 1, theta 2, and let us see when it is an arbitrage opportunity. We must have the value at 0 less than or equal to 0, and the value at by the way, that is equivalent to theta 1 plus theta 2 less than or equal to 0, and the value at 1 to be non-negative in every state and positive in at least 1. Now there are only two states here, so 1 plus I theta 1 plus U theta 2 is greater than or equal to 0, and 1 plus I theta 1 plus D theta 2 is greater than or equal to 0. Now, if theta 2 is greater than or equal to 0, then since 1 plus I is more than 1 more than D, we have theta 1 is less than or equal to 0, and D theta 2 is greater than or equal to minus 1 plus I, theta 1 greater than or equal to D, theta 1 greater than or equal to D, theta 2. This implies that both theta 1 and theta 2 are 0. So there is no arbitrage opportunity. However, if theta 2 is less than 0 and theta 1 is greater than 0, and 1 plus I theta 1 is greater than or equal to minus U theta 2 greater than or equal to U theta 1, therefore 1 plus I is greater than or equal to U. Since minus U theta 2 is greater than minus D theta 2, the third inequality is strict, and theta is an arbitrage opportunity. Note that if we start with the assumption that 1 plus I is greater than or equal to U and choose theta 1 equal to 1 and theta 2 equal to minus 1 plus I over U, which is less than or equal to negative 1, then theta is an arbitrage opportunity. I actually wasn't very happy with those notes that I showed you there. It's a bit unclear, so I created a specific set of notes specifically for a two-dimensional market, and I want to go over this with you. So if we have S of 0 equal to 1, 1, and payoffs at time 1, 1 plus I, and UD. In other words, the first security has a price of 1 at time 0, and so does the second. The first security is risk-free, and its payoffs at time 1 are 1 plus I or 1 plus I, but the second security is risky, and its payoffs at time 1 are either U or D, referring to up and down. Now we typically assume that U is more than D. One of them has to be different than the other, otherwise these two securities would be two risk-free securities. And then that would not be a market with two linearly independent securities. So we want a two-dimensional market, meaning two securities that are linearly independent in their payoffs. So we will derive the conditions for this market to be arbitrage-free, given that U is more than D. But of course you could assume that D is more than U, but then you just change the names, and the up security is U, and the down security is D. That's all. So here is a discussion of this. Allow U to be less than or equal to 1 plus I. Create a portfolio of 1 unit of first security and negative 1 unit of second security. The current price will be 0. We assume there are no trading costs, no taxes, things like that. And you can buy anything and short anything. So current price is 0, 1 minus 1. Payoffs at time 1 are in U state 1 plus I minus u, which is greater than or equal to 0, if u is less than or equal to 1 plus I. And in D state, 1 plus I minus D greater than 1 plus I minus u, because u is more than D, which is greater than or equal to 0. Now notice this, that because there is a strict inequality in this chain of inequalities in D state, this means that there is a positive payoff in that state and non-negative payoff in the up state, and so this is an arbitrage. So u less than or equal to 1 plus I can't happen if the market is arbitrage free. Now allow D greater than or equal to 1 plus I. Create a portfolio of 1 unit of security, of second security, and negative 1 unit of first security. Current price is 0. Payoffs at time 1 a negative 1 minus I plus u, which is greater than minus 1 minus I plus D, greater than or equal to 0. And then in D state, negative 1 minus I plus D, which is greater than or equal to 0. So this is an arbitrage. And so if the market is arbitrage free, D being greater than or equal to 1 plus I can't happen. Therefore, we have shown that if the market does not allow arbitrage, u less than or equal to 1 plus I can't happen, and D greater than or equal to 1 plus I can't happen, and therefore in an arbitrage-free market, D is less than 1 plus I, less than u. Now suppose that the market is not arbitrage-free. There is a portfolio which is an arbitrage, so security with a non-positive price with a non-negative payoff, and a positive payoff in at least one state of the world. And let us write alpha beta for that payoff at time 1, and let us first assume that alpha is greater than 0 and beta is greater than or equal to 0. Now you can do it the other way around too, but it really doesn't make any difference. So you can take beta positive and alpha greater than or equal to 0. The securities payoff alpha beta would be a linear combination of 1 plus I and u d, because 1 plus I and u d are linearly independent, and two vectors form a basis in a two-dimensional vector space. So let us write a and b for the coefficients of that linear combination. And it has to be that alpha is equal to a times 1 plus I plus b times u, and beta is a times 1 plus I plus b times d. And then I use the Cramer's rule to solve for alpha and beta, whatever way you do it, solve for alpha and beta. Most textbooks or classes no longer teach Cramer's rule. It's a formula for a solution of a system of two linear equations that have a unique solution, and you can look it up. It's C-R-A-M-E-R. I believe he was Swiss. Kramer was a mathematician from the 19th century, I believe. Well, you can look it up. It's not that important. Just solve the equations, the system of equations. And you will get a equal to 1 over 1 plus I times beta u minus alpha d over u minus d, and b will be equal to alpha minus beta over u minus d. The price of this security today is a plus b, which we can write then therefore as 1 over 1 plus I times beta times u minus 1 plus I plus alpha times 1 plus I minus d over u minus d. If the price today is non-positive, then, well, 1 over 1 plus I, that's positive, u minus d is positive, so it has to be that this numerator is less than or equal to 0. But both alpha and beta are non-negative, which implies that either u minus 1 plus I or 1 plus I minus d, or both of them have to be negative. This shows that the condition d less than or equal to 1 plus I less than or equal to u, with at least one of the inequalities being strict, is equivalent to the market being arbitrage-free. But let us note also that d equal to 1 plus I less than u, or d less than 1 plus I equal to u, allows for arbitrage, because in the first case you can short the first security by risky security, and your payoff is either 0 or u minus 1 plus I, and in the second case short the risky security and buy the risk-free security, getting either 0 payoff or 1 plus I minus d payoff. In other words, for two securities, risk-free one and risky one, no arbitrage is completely equivalent to the risk-free payoff lying strictly between the worst-case scenario payoff of the risky security and best-case scenario of the payoffs of the risky security. It can't be this way that one of the two securities is always better. You beat the risk-free security in the up state and you lose to it in the down state. That's what arbitrage in such two-dimensional market means. Now we'll introduce a concept of a state price vector. It's a vector whose entries are all positive such that S of 0 is equal to psi, this vector, times S of 1 omega, that is Sj of 0, which is the price today of the j security, is the sum from k equal 1 to m of psi k S sub j of 1 omega k for a j equal to 1, 2 through n. The above expression may not be unique if there are fewer than m assets with linear independent payoffs at time 1. And the reason is pretty straightforward, that it's a system of equations, and if the system like that has a unique solution, a linear equation, so has a unique solution if and only if the matrix of the system has maximum rank. And if there are fewer than m assets with linear independent payoffs at time 1, then that's not the case. So this is n securities, n securities, m states of the world, and the situation where you can get this kind of a unique solution is actually the situation where there are enough linearly independent securities to have for them to have m prices just as many as those states of the world at time 1. Note that a security which pays 1 in a given state of nature, a state of the world, and 0 in all other states is termed an Arrow-Debreu security. And let's write E1 through EM for that. So E1 pays 1 in state 1 at time 1 and 0 in all other states. E2 pays 1 in state 2 and 0 in all other states through EM. That's a standard basis for m-dimensional Euclidean space. These are the payoffs of the Arrow-Debreu securities. And this is kind of the key result that I want you to know, the fundamental theorem of asset pricing. The single period securities market model is arbitrage-free if and only if there exists a state price vector. In other words, the value of security j at time 0 can be obtained by taking the value of each possible state at time 1 and multiplying it by the corresponding entry of the state price vector. The state price vector is similar to NEX in life contingencies, a combined discount factor that takes probability and interest into account. Now, this proof here is not really that relevant to you because I won't test you on this. We will do exercises on this topic. Suppose that that a state price vector exists. If for some trading strategy S of 1 omega times theta, that trading strategy, is greater than 0, then S of 0 times theta, which is psi times S of 1 omega theta, is greater than 0 because the state price vector is strictly positive. Remember, we're assuming that the entries in the state price vector are positive. And basically, the state price vector consists of prices of securities which are the Arrow-Debreu securities. So this implies that the market is arbitrage-free. Now suppose that the market is arbitrage-free. We now only consider a proof in the case when there are m assets for linear independent payoffs at time 1. If there aren't, the market is incomplete and you would need to complete it, and we'll actually do an exercise on this. then S of 1 omega has full rank and n is greater than or equal to m. Assume that the first m assets are linearly independent. Write S of 0 as L of 0 and then followed by R of 0, where L of 0 are those securities that are linearly independent at values at time 0, and R of 0 are the other ones. The same way, write S1 of omega as L1 followed by R1, and then they are the payoffs of those securities. The matrix L of 1 is invertible because we assume that these guys are linearly independent, and define psi to be L of 0 times L of 1 inverse. For an Arrow de Bruce security with payoff EM, consider the trading strategy defined as theta equal to L of 1 inverse times EM transpose with zeros following that. Then S of 1 omega times theta is L of 1 times L of 1 inverse times EM, and that's EM. Since this is a positive payoff and the market does not allow arbitrage, it follows that S of 0 times theta, which is L of 0 times L of 1 inverse times EM, or psi EM is strictly positive. This implies that the nth component of the vector psi is strictly positive, and as m was arbitrary, this applies to all components. Now consider psi S of 1 omega, which is L of 0, L of 1 inverse, multiplied by this L of 1 followed by R of 1. So that's L of 0 and then followed by L of 0, L of 1 inverse, R of 1. If n is m, the second part of this matrix does not exist when we found the state price vector. If n is more than m, then since the columns of L of 1 form a basis for this vector m-dimensional space, then there is an m by n minus m matrix K such that R of 1 is L of 1 times K. Because the model is arbitrage free, the prices of the n minus m redundant securities, those in that R part that follows L, must equal the cost of the unique portfolio of the linearly independent assets that produce the same payoffs at time 1. So R of 0 must be L of 0 times K, of psi L of 1 K, of psi R of 1. Therefore, psi of S of 1 omega is psi L1 times L1 followed by R1, and that's psi L1 followed by psi R1, and that's L of 0, R of 0, so it's S of 0, and so this ends the proof. So here is again that simplest case, two securities, market, bank account, and the stock. The stock either goes up to U or down to D after one period, and the same notation as before. Then using the state price vector concept, we get the system of equations. 1 is equal to 1 plus I psi 1 plus 1 plus I times psi 2, as the bank account is always worth 1 plus I. So the payoffs at time 1 are always 1 plus I. And 1 is equal to U psi 1 plus D psi 2 for the stock. And we just solve it for psi 1 and psi 2. And psi 1 is 1 plus I. It would be nicer if I should have put 1 plus I in parentheses, but it's 1 plus I minus D over 1 plus I times U minus D. And psi 2 is U minus 1 plus I in parentheses. The parentheses don't look very good, but they are there, over 1 plus I times U minus D. Notice that if 1 plus I is greater than U, then there is an arbitrage, since this would mean that psi 2 is negative. To make this example more specific, and by the way, that's one of the simplest ways to tell if the market is not arbitrage free. If you try to solve for the prices of Arrow de Bruce securities and you get negative values, and that means that the market allows arbitrage. So suppose that a stock with price 1 now can increase to 1.20 or decrease to 0.80 after one period. If the one period risk-free interest rate is 10%, and S of 0, we assume that both securities, risk-free and risky, are worth 1 today, and after one period, the risk-free security will be worth 1.10 with risk-free interest rate of 10%. in the upstate and in the downstate. But the risky security will be worth 1.20 in the upstate and 0.80 in the downstate. And then, based on the formulas we just derived, psi1 and psi2, the state price vector, is 1.10 minus 0.80 over 1.1 times 1.20 minus 0.80, and 1.20 minus 1.10 over 1.1 times 1.20 minus 0.80. So it's 30 over 44 and 10 over 44. These are the prices of payoffs of 1 in a specific state of the world and 0 in all other ones. So in the upstate, if you paid $1 in the upstate and nothing in other states, then in today's money that's worth 30 over 44, and in the downstate, payoff of 1 and 0 in other states, that's worth 10 over 44 in today's money. If there is a state price vector, now we're going to define a new concept, Q of omega k equal to 1 plus I times psi k. Then Sj of 0, it actually is equal to the sum over all values of omega over all states of the world of Q of omega Sj of 1 omega over 1 plus I. The values Q of omega define what is called the risk-neutral probability measure on omega. The risk-neutral probability measures are strictly positive and add up to 1, so this is a probability measure. Now come back to the basic example with two securities and two states, up and down for a stock, bank account, and a stock. Using previously calculated state price vector, we get Q, or probability of an upstate, written as Q1, as 1 plus I minus D over U minus D, and Q down as Q2, U minus 1 plus I over U minus D. Now the generalized version of the fundamental theorem of asset pricing says that the following are equivalent. The single period model is arbitrage free. There exists a straight price vector, or there exists a risk-neutral probability measure. Now let x of omega be the payment made by security x at time 1 if state omega occurs. And assume that we do not have the market price for this security, but we can replicate it with securities that have market prices. To find its price, we try to calculate, to create a portfolio such that that portfolio is equal to x of omega at this omega in value for all omega in the big omega. This portfolio that has the same payoffs as the given security is called a replicating portfolio. Now obviously, if you believe in principle of no arbitrage, two securities that make exactly the same payments have the same price. That's actually a very important principle. Two securities that have exactly the same payments in the future must have the same price, even if they happen to have different names. It doesn't matter. I call this Mr. Philip principle. Mr. Philip was my mathematics teacher in elementary school when I grew up in Poland under communism, and Mr. Philip was a great guy because he always came to class and told us anti-communist jokes. So one day he came to class. Oh, I should tell you also that we were taught that everything ever invented was invented by Soviet and Russian scientists. And we thought, of course, that was a joke, but it couldn't be. We didn't believe it at all with all this propaganda. But I have to tell you that one day I found out to my astonishment that Mendeleev actually did come up with that periodic table, that was real. Oh well. So anyway, this story is that my mathematics teacher came and said to us very seriously that the Soviet scientists invented a new kind of raspberry. And it is as big as a strawberry, and it smells like a strawberry, and it tastes like a strawberry, and it has the same consistency as a strawberry. And then he became silent, sat down, and all the kids were thinking about what in the world did he mean. So I call this the strawberry principle because what he meant was that, hey, if it walks like a duck and talks like a duck, it's a duck. It wasn't a new kind of raspberry, it was a strawberry. So the portfolio that you create that makes the same payoffs as the security that you're analyzing is called a replicating portfolio. And we say that any security that can be replicated by some trading strategy, we say that it's attainable. The time value of x is psi times x, where psi is the state price vector, so prices of those Arbitrage securities, and that's equal to the sum over all omega in the set of states of the world of q of omega times x of omega divided by 1 plus I. So this is an expected present value because the q's are probabilities, and x of omega divided by 1 plus I is present value. So the price is the actuarial present value of future cash flows. If there are two states, psi x is equal to q1 times x of omega 1 divided by 1 plus I, plus q2 times x of omega 2 divided by 1 plus I. Now we say that a market is complete if all securities can be replicated. A single period is this theorem that you need to know. A single period arbitrage-free market is complete if and only if there is a unique state price vector. A single period model in which security 1 is riskless is arbitrage-free and complete if and only if the risk-neutral probability measure is unique. So consider the following market, for example. At time 0, we have prices of 1 and 1 for two securities. And at time 1, there are 4 possible states of the world. The first security makes a payment of 2 in all of them. And the second security makes a payment of 0, 0, and 4 in the third state of the world, and 3 in the fourth. So there are two assets, a riskless one and a risky one. Each costs 1 initially. The riskless asset grows to $2 at the end of the period, regardless of the state, and the second security's value at the end of the period is 0 in states 1 and 2, 4 in state 3, and 3 in state 4. Let us find the state price vectors. So we write out the equations we would write. 1, the price of the first security has to be this linear combination of payoffs of the first security multiplied by prices of the states. Payoff in state 1 is 2, and the price of state 1 is psi 1. Payoffs of state 2 is 2, and the price of state 2 is psi 2. Payoff in state 3 is 2, and the price of state 3 is psi 3. Payoffs in state 4 is 2, and the price of state 4 is psi 4. And we do the same for the second security. 0, 0, 4, 3 are the payoffs, and the price is psi 1, psi 2, psi 3, psi 4. There are 2 equations and 4 unknowns, and we end up with a parametric solution. Set psi 2 equal to s and psi 4 equal to t. Then 1 is equal to 2 psi 1 plus 2s plus 2 psi 3 plus 2t, and 1 is equal to 4 psi 3 plus t, or 1 minus 3t is 4 psi 3. Solving for psi 3, 0.25 minus 0.75 t. Psi 1 is 1/2 of 1 minus 2s minus 2t minus 2/4 times 1 minus 3t. And that ends up being 1/4 of 1 minus 4s minus t. Since prices must be positive, prices of Arbitrage securities, so we must impose some conditions on s and t to ensure that. Since psi 2 is s and psi 4 is t, we have s is more than t, s is more than 0 and t is more than 0. Also, psi 3 is 1/4 of 1 minus 3t, so t is less than 1/3. Finally, psi 1 is 1/4 of 1 minus 4s minus t, so 4s plus t is less than 1. The market is not complete, as you can see. The state price vector is not unique. We have many solutions. Not being complete means that some securities do not have market prices. We will try to complete it. Consider a security with time 1 payoffs 1001. Let us see what its price should be while still maintaining the absence of arbitrage for this model. By the definition of a state price vector, psi times c, the security, is 1 psi 1 plus 0 psi 2 plus 0 psi 3 plus 1 times psi 4. So we plug in what we know about psi 1 and psi 4. We get 1/4 minus s plus 3/4 t. This is a linear expression in s and t, and we can find its range of values, not ITD, but that should be s, a range of values on the area where s and t are allowed to be. This is a simple linear programming problem. The maximum value of 1/2 is obtained as t approaches 1/3 and s approaches 0. The minimum price of 0 is obtained as t approaches 0 and s approaches 1/4. In the second example, we will add 2 more assets while preserving the arbitrage-free nature of the model. So the existing market, in this case, is 1, 1, and then 1, 1, 1, 1, and 0, 1, 0, 3. Now you see the risk-free interest rate in this market is 0. In order to do this, each time an asset is added, the range for asset price must be chosen to preserve the arbitrage-free nature of the model. We can do it like this. The minimum price of the new asset is calculated by first forming a portfolio from the existing assets that is always dominated by the new asset. Then the new asset must sell for at least as much as the maximum price of this portfolio. Or the maximum price of a new asset is calculated by first forming a portfolio from the existing assets that always dominates new asset. Then the new asset must sell for no more than the minimum price of this portfolio. The first security to be added to the model is this Arrow-Debreu security E1. Generally, that's what you do when you want to add securities to complete the market. You use Arrow-Debreu securities because they are the simplest ones. So to find the minimum price, we must solve the following problem. Maximize theta 1 plus theta 2 subject to theta 1 less than or equal to 1, theta 1 plus theta 2 less than or equal to 0, theta 1 less than or equal to 0, and theta 1 plus 3 theta 2 less than or equal to 0. The optimum in linear programming is always achieved at the corner point of the constraint region, so we need to find all corner points and values of the objective function at them. And for the problem above, there are 6 corner points, and we have these theta 1, theta 2 for them. So now determine theta 1 plus theta 2 at all valid points, which in this case is only the point 0, 0, and the minimum price of the new security is 0, which we kind of knew. To find the maximum price, we must solve the following problem. Minimize theta 1 plus theta 2 subject to theta 1 greater than or equal to 1, theta 1 plus theta 2 greater than or equal to 0, theta 1 greater than or equal to 0, and theta 1 plus 3 theta 2 greater than or equal to 0. And then we get this table of possible values, and the solution is found as theta 1 equal to 1 and theta 2 equal to negative 1/3, and the maximum price is 1 minus 1/3, which is 2/3. And actually the new asset may be added at any price in the interval from 0 to 2/3, which is a very peculiar property. It mathematically shows you that if you bring in a new security to the market and that security is not linearly dependent on what people trade, then we don't really know, literally don't know, what the proper price for that security is. And the reason for that is related to the what you studied in the equilibrium-based models, that you really know the prices when people start trading, when people reveal their preferences. There is a range of possible values, but there isn't one number. You need to start trading for people to really tell you how much they prefer this thing to other things. You can continue to add securities one at a time, continuing in this fashion until the number of securities equals the number of possible states at time 1. However, it becomes very difficult to solve for the price range manually after the third security, since there will be more than two variables in your constraints, this will generally require programming or optimizing software. Once the number of securities equals the number of possible states at time 1, you can solve for a unique state price vector that will serve as a state price vector for the original model as well. This model that we talked about, well, it's simple, it's only one period, can be generalized to a multi-period discrete model with m states of nature, like before, but they are now paths of possible futures, and t plus 1 time points, k equal to 0 through t. There are n assets, and Sj of k is the value of security j at time k. The one-period interest rate for the riskless asset, if such an asset is available, is assumed to be Ik equal to S1 of k plus 1 over S1 of k minus 1. So notice that it's a different risk-free interest rate at each time. In the next section, we'll discuss the binomial form of this model. So assumptions are investor observe all prices and remember all the past and present. The binomial model, you know, of course, from what we talked about before, so we don't even have to discuss it. The binomial model is covered in exam IFM, was covered in exam MFE, and it's covered in Mathematics 383. And there is a relationship of binomial model to what we're talking about because both are an attempt to create arbitrage-free models. The investors start off at time 0 with full knowledge about all possible states of the world, probabilities, and the values of S, J, K, omega for all J, K, and omega. The price Sj of 0 omega is constant with respect to omega. For the investors at time 0, any omega is possible. There's a unique simple path for each omega, sample path. So it's a path of the future. So at time t, the investors know the true state of nature. Finally, at intermediate points in time, k less than t, no additional information is given to the investors that would help them learn the true state of nature. They know the past, they know the future in terms of probability distribution, but they don't know what will happen. The information known by investors at a point in time can be used to partition the possible states into ones that are still possible and ones that can no longer be possible. These subsets are called histories. They can then use this information to modify construct trading strategies, they being the investors. The value of portfolio under a specific trading strategy at time k, immediately before any transactions are made, is V theta, depending on the trading strategy, k minus omega equal to S of k omega times theta of k minus 1 omega. So the value of each security at time k times the number of shares of each security held at the prior time period. The value of the portfolio immediately after any transactions are made is V theta k omega, so without the minus now, equal to S sub k of omega times theta k omega. So the value of each security at time k times the number of shares of each security held at the current time period. The net cash flow out of the portfolio, C theta k of omega, is minus V theta k omega if k is 0, because you spend money to buy the portfolio, so you have negative money, negative cash flow, negative money flow, because you're spending money. And V theta of k minus omega minus V theta of k omega if k is greater than or equal to 1, less than or equal to t minus 1. Notice that we don't do anything at any point in time except for the integer values. A trading strategy is self-financing if C theta k omega is 0, for k greater than or equal to 1 less than or equal to t minus 1. This means that no money has come in or out of the portfolio except at the beginning, at the end. We say that a multi-period securities market admits arbitrage if there is a self-financing trading strategy called an arbitrage opportunity, denoted by theta, such that v theta of 0 is less than or equal to 0, so it doesn't cost any money. A v theta of t is s of t times theta of t minus 1 is greater than or equal to 0, and it's not equal to 0, meaning that it has positive payoffs in some states and non-negative in all states. So basically, the initial cost of a portfolio is 0 or less. A strategy is self-financing. No money comes in or out in the intermediate periods of time. And the payoff at time t for this strategy is non-negative in all states and strictly positive in at least one state. The idea is again that without any investment, one earns a riskless profit. There will be now two important concepts used in the definition of the risk-neutral probability measure. Normalized prices of assets follow a discrete stochastic process. Normalized means that they're divided by accumulation of a risk-free asset investment of 1 up to the point at which you calculate the price. So you put $10 in, and the value of the asset divided by 1 plus risk-free interest rate to the time t that it applies in the future, that's the normalized price. So it's not the price, it's the price, the ratio of the price to what you would have if you invested risk-free the same amount of money. The process is called adapted if investors who know the past and present prices of securities know the current prices of a given normalized asset we are considering. That process is called a martingale if it is adapted and the expected value of future normalized price is the current normalized price. So in general, a stochastic process is a martingale if the expected value of what it will be in the future is its value today. And that martingale here is the process of normalized prices of securities. A risk-neutral probability measure on omega, which now consists of paths, not just single events, is a probability measure assigning positive probability to each omega in big omega, and such that the normalized price of each security is a martingale. A stochastic process, psi, is the state price process if the sum of over all omega of psi of 0 omega is 1. It is adapted, it is strictly positive, and the sum over omega in H history of psi k omega sj k omega is equal to the sum over omega in H of psi k plus 1 omega sj k plus 1 omega for all time k histories, all k and all j. Then the multi-period fundamental theorem of asset pricing says that for a multi-period model of a securities market that satisfies the assumptions of this section, the following are equivalent. The model is arbitrage-free, there exists a straight price process, there exists a risk-neutral probability measure. Now, valuation of European options and other cash flows. Now, we do European right now because we don't allow any trading at intermediate steps, and of course American options can be exercised early, but here no such trade. So European option or other set of cash flows is valued by creating a replicating portfolio and then finding the price of the replicating portfolio, assuming the option or other set of cash flows is attainable. Completeness in the multi-period model. Remember, completeness refers to the situation where every security is attainable, or basically everything that can be traded is traded and we can find the price. An arbitrage-free multi-period model is said to be complete if every adapted cash flow stream C is financed by some trading strategy theta. For an arbitrage-free multi-period model, the following statements are equivalent. The model is complete. The state price process psi is unique. The risk-neutral probability measure Q is unique.